So indeed, as advertised, the title of my talk today is the Muon-Smasher's Guide, and exactly what that is, I'll try to explain in the course of the talk. And I just also like to thank, of course, Daniel for a very beautiful introduction to some of the accelerator and detector physics, which I'll try to build on in discussing aspects of the theory case. So there's a sort of, it's unavoidable to notice that there's been an enormous uptick in activity, both theoretical, experimental, and accelerator-based, surrounding muon colliders in the last year or two. And that is due to a number of reasons. Obviously, one is sort of a series of progress on the accelerator side, starting with MAP and more recently with MICE and the Lemma proposal, as well as the formation of the muon collider collaboration. The interest that was generated in the European strategy update, but also in the United States as we're approaching the SNOMAS process, which was supposed to culminate this summer, but as it is planned now because of COVID, will culminate next summer. In the process of SNOMAS activities forming interest in a muon collider and potentially what the US could contribute to that program has been growing enormously. And so there's a real opportunity to seize this energy and to build significant momentum. And I think as a theorist, what's particularly compelling right now is that it's sort of a clear slate as far as developing the physics case. And that is to say, I think when it came to the round of proposals for future colliders that we currently have for Higgs factories and proton-proton machines, we sort of had to evolve out of a pre-LHC and pre-Higgs discovery mental framework as to what we cared about in future colliders. And that has been done over the process of the last decade. But with the muon collider, we now sort of have understood some of the physics questions we're interested in after the Higgs discovery. And we really have a chance to start from zero in terms of understanding what a muon collider can offer. And so we're not just recapitulating existing physics cases, but actually coming up with interesting new ideas. And as I hope I'll be able to communicate in this talk, apart from just the opportunity to do something new, when you actually look at it, assuming that we can achieve the accelerator and detector parameters that Daniel has laid out, which is very encouraging, that the physics itself is sort of the best of all possible worlds, because it erodes this sort of dichotomy that we've developed in thinking about future colliders, that either you get energy or you get precision. And in fact, at a muon collider, you can get both. So on the right-hand side of the slide, this is just a poster that my students made. So as we started to get interested in this, really last June and July, we actually started out with a hackathon in my group and brought in some collaborators from elsewhere to just start generating numbers and understand what the terrain looked like. And so we called that the Muathon. And so my students made this poster for that effort. So what I'll tell you about mostly today is, as Filippo mentioned, the product of that sort of has grown out of that Muathon effort that we're calling the Muon-Smasher's Guide. And this is a collective of about 40 theorists and some experimentalists. Although there are many people in the United States, we're also in this effort involves theorists in particular from Europe as well. And the idea was just, this is not an effort that is seated within the MCC. This is not seated officially in SNOMAS. It was really just the product of some of us getting together and being curious about what the landscape of physics possibilities looked like, and wanting to at least try to sketch out for ourselves and for those who are interested what novel opportunities might not have been considered thus far. So this document, which hopefully will appear any day now, has a very coarse-grained approach, just interested in sort of blocking out what the landscape of rates and processes looks like, and does not treat in great detail things like beam-induced backgrounds and reconstruction issues, which of course are going to be central towards the full development of a physics case. But the goal of the guide is to sort of sketch, what if you, rather than starting with some design, if you just ask, of all the possible energies and luminosities, with some priors about more energy and more luminosity being challenging, in that giant space, what region of that space gives you a physics case that is really qualitatively new and possibly could give us most of the things that we are interested in a post-LHC era? And so in this document, we sort of take a look at many different luminosity assumptions and center of mass energies that include both sort of existing proposals, including the ones that Daniel mentioned, as well as just some more ambitious possibilities. And to sort of try to bracket the physics case, in many cases, we think about both an optimistic integrated luminosity, which is designed to compensate for the 1/s fall off in rate, as well as a conservative integrated luminosity assumption, which just assumes that you can never get more than 10 inverse Atterbarn. And that helps, in that range of luminosities, hopefully brackets the physics case at various center of mass energies. So what I want to do is just really talk about, rather than many specific models, although I will get to some specific examples, I want to sketch just broadly speaking how it is one as a theorist, at least approaching the physics case, can think about what is on offer from a muon collider. And I think the most striking thing, which of course Daniel showed a version of it from the European strategy update documentation, and there was also a nice version of it by Maltoni and collaborators last year, you can simply ask what is the equivalent center of mass energy of a muon collider and a proton-proton machine. And depending on exactly how you set up this question, it can look extremely favorable for muon colliders. So what these plots are showing is if you just look, imagine you're producing new physics at some mass scale. At a muon collider, you imagine very favorable circumstances where you are making collisions just above threshold. At a proton-proton machine, of course, you are not able to do that because your PDFs have fallen off by then. And then you can ask, depending on whether the production mode you're engaged in is 2 to 1 or 2 to 2 of new physics, you can then ask, what is the equivalent energy of a proton-proton machine that gives you the same cross-section as a muon collider. And so that's what's just shown in these plots. The different bands correspond to just choosing different PDF sets to show the dependence on PDF assumptions. And the dashed and solid lines are just imagining the possibility that there could be some underlying partonic differences in the cross sections. For example, QCD initiated processes at a proton-proton machine versus electroweak initiated processes at a muon collider. But the conclusion is, depending on what type of processes and what the initiation is, there are indeed factors of 10 in the relative center of mass energies to give you equivalent cross sections. Okay. And so this aspect of a muon collider is benefiting from the fact that you are able to collide elementary particles rather than composite objects. And so you're able to access this incredible energy gain. But what's really compelling about muon colliders is not only are you colliding elementary particles, but they also at the same time are surrounded by a virtual cloud of electric bosons. And so the fusion of those bosons gives you a completely complementary production mode to the annihilation, and one that is important at sort of smaller partonic X. So these are just nice plots taken from a paper last year by Tao Han and collaborators that illustrate this very nicely. I want to just mention some qualitative features of these, but also I'll go into some ways to think about what is going on in these plots in the next 2 slides. So on the left, this is just showing a variety of different production modes, including the annihilation channels where muons annihilate in the S channel. Those are the ones that fall as 1 over S. And then there are VBA production modes, which are the ones, VBF production modes, which are the ones that sort of grow logarithmically with square root of S. And the other thing that you see in this plot is there's solid lines and dashed lines. The solid lines are VBF cross sections computed using the effective photon approximation, or the Weizsäcker-Williams approximation. And the dashed lines are ones that you get by instead using integrated parton distribution functions for the muon. And you can tell from this, there's a factor of few, apparently difference between these cross sections. I want to talk a little bit about that in a minute. But the other thing, of course, that is just apparent is that VBF cross sections, although at small center of mass energies, they're subdominant to annihilation, they eventually grow by orders of magnitude to become the most important, at least for standard model processes. The other thing you can conclude, looking on the right panel, which is just the PDFs themselves, is that, of course, by orders of magnitude, the dominant contributions are from the neutral gauge bosons, followed with some suppression by the transverse Ws, and then significantly further suppression by the longitudinal Ws. And you might conclude from this that primarily the vector boson fusion processes at a muon collider are gamma-gamma fusion, for example, and WW fusion is less important, longitudinal collisions even less so. But these conclusions, it's important to think a little bit more deeply about what happens in an actual physical process. And as we'll see, for one reason, one important fact is that these are just the PDFs. The reason, for example, the photon PDF is the largest is it has the largest logarithmic enhancement, of a log starting at the mass of the muon, running up to your energy of interest. But when you're actually considering physical processes with reasonable cuts, that log gets cut off, and that actually puts the contributions from WW fusion onto comparable footing. So there's a lot of rich and interesting physics going on here, but it's shaped both by the underlying PDFs of the muon as well as the final state that you're examining. So just to comment on, if you're a theorist and you would like to calculate some rates for a muon collider, do you need to use the PDFs, or can you use something like the effective vector approximation? Because in this previous slide, it looks like there's a factor of few difference between the two for vector boson fusion. And the answer is actually, if you dig into it, thankfully, it's pretty easy to get the good back of the envelope numbers. And the reason is the following: that when we normally say the effective vector approximation, the original effective vector approximation, the logarithm in that is a logarithm of the muon energy. But of course, if someone got you out of bed early in the morning and said, come up with an effective vector approximation, you wouldn't put the energy of the muons in the logarithm. You'd put the energy of the vector bosons in the logarithm, because that's the appropriate scale in this case. And so it turns out, if you pick an intermediate prescription, which is instead of using the effective vector approximation as originally sort of framed in the Weizsäcker-Williams approximation, if instead you just use sort of the leading logarithm PDF, where the scale is the scale of the vector bosons, that actually does a very good job of reproducing the cross-section that you would get by doing more fully resummed PDFs. Okay, so just as a theorist, this is a lesson that you don't have to generate incredibly elaborate PDFs in order to get reliable cross-section estimates for VBF. So I've sort of tried to establish there's two interesting sets of processes for both standard model and beyond the standard model physics, right? There's production and annihilation of the muons, and there's production and vector boson fusion. And the fact that annihilation falls as 1/s, whereas VBF grows logarithmically with energy, might suggest to you that all of the interesting physics at a muon collider is going to happen in vector boson fusion. But that's not quite true, because although VBF is growing with logarithm of your center of mass energy, it's also typically suppressed by the square of the mass scale of the new physics. And so if you're actually doing a search for new physics, then as you get closer and closer to threshold for the new physics that you're producing, the annihilation cross-section wins out again. And so that's just illustrated in these plots here. This is just showing for an SU2 singlet with hypercharge 1, or an SU2 doublet with hypercharge 1/2. These are vector-like fermions. You can just compute the ratio of the annihilation cross-section and the VBF cross-section. And indeed, if you're far away from threshold, if your mass scale is less than 10% of your collider energy, VBF wins out for all of your interesting center of mass energies. But as soon as your mass scale goes above about 10% of the collision energy, then the annihilation becomes the dominant mode. And so even though annihilation is falling as 1/s, at the end of the day, if you're producing new physics with a distinctive final state, as long as your cross-section is tens of Autobarn, and you have tens of inverse Autobarn of integrated luminosity, you'll be able to discover an annihilation rather than vector boson fusion. So this is just an important message that if you're thinking about standard model physics, vector boson fusion is the most interesting mode on rate grounds alone. If you're thinking about backgrounds, vector boson fusion is typically the most interesting. But if you're thinking about discovery of distinctive final states, then annihilation is really the place to look. And that's just sort of made clear by this simple example. So this is the result of a very simplified analysis where we just look at parton level and don't worry about the reconstruction of the top quarks in the final state. But as an example, you can, for example, look for the pair production of stops in, say, supersymmetry, and consider the leading backgrounds from VBF TT bar production, and ask the question with sort of nominal cuts, is it possible indeed to discover these up to their kinematic threshold in annihilation? And so the result of this simplified study, which of course requires a lot more to make it fully realistic, is indeed, because you still have sufficient cross-section very close to threshold, as long as you have tens of inverse Autobarns of integrated luminosity, you're really able to discover new physics up to threshold. So that's just a nice validation of your expectation that as long as your final state is distinctive in new physics, you should be able to reach all the way up to threshold. Another message that's very important in the search for new physics is that despite what you might conclude from looking at the PDFs, a muon collider is actually a longitudinal vector factory. So again, I say despite what you would conclude from looking at the PDFs, in the left panel, this is showing now the luminosities, the parton luminosities. And this has a similar conclusions to what you would have gotten from looking at the PDFs themselves, is that the luminosities are by far the greatest for the neutral vectors, followed by transverse Ws, and then much suppressed by several orders of magnitude are the longitudinal Ws, right? Just because the longitudinal Ws couple very weakly to the muon. So you might conclude from that fusion of longitudinal vectors is unimportant. But there's a variety of effects. One is that, of course, in realistic phase space, cuts actually change the relative contributions of these luminosities. And finally, at the end of the day, a cross-section is the convolution of some partonic amplitudes with these luminosities. And those partonic amplitudes, as we know, typically promote with energy the longitudinal contributions. And so that's manifested in the right panel, which is just looking at the diverse contributions to TT bar production. And you see at the end of the day, when you actually get to the cross-section, the longitudinal contribution to TT bar is very significant, despite the suppression in the luminosities. And so that's just a sign that muon colliders, despite the small coupling of the longitudinal vector to the muon, are really an extraordinary laboratory for longitudinal vector physics. And this is, I think, what drives a lot of the really unique opportunities that we get in a muon collider compared, for example, to a 100 TeV proton-proton machine. Because although you have vector boson fusion at 100 TeV proton-proton machine, it's a small fraction relative to backgrounds for many interesting final states. Whereas, at a muon collider, it is an order one. I mean, the signals and the backgrounds are all of the same order, and so you have enormous longitudinal vector boson fusion signals that you can put to good use. So I just want to give you a variety of examples of that. The first is maybe the one that everyone cares about the most in the post-Higgs discovery era, which is what you can do with Higgs physics. And although the cross sections for Higgs production at a muon collider are much lower than comparable cross sections at a proton-proton machine, nonetheless, of course, the thing that's really important is the relative size of the backgrounds. So this is just an illustrative plot, but it's showing you as a function of the center of mass energy of your collider, the cross section for single Higgs production, either in VBF or with other inclusive final states, relative to a total cross section. And here the total cross section is sort of chosen to be representative of the size of backgrounds. So for a muon collider, the relevant backgrounds that dominate are vector boson fusion to single bosons. Whereas at a proton-proton machine, I'm just taking the PP to BB bar cross-section as the background. And of course, you see the many orders of magnitude difference, which is relatively flat as a function of center of mass energy. And so this is the sign, of course, that we expect to be able to do very interesting Higgs physics in a muon collider, even though the cross-sections are not necessarily as large. So to my knowledge, there is no current sort of comprehensive projections or fits for a muon collider. There are lots of reasons for that. So in the Muon-Smasher's guide, we're making what I would call a first sketch of what some of the Higgs precision might look like. So what do I mean by sketch? So this is the result of just doing fast sim and the Delphi's muon collider detector card that Daniel talked about. Very minimal cuts. That's just to get the acceptances and efficiencies. And these acceptances and efficiencies are pessimistic in the sense that, for example, there is no acceptance in forward regions apart from muons in the current detector card. And so you could certainly imagine increasing these acceptances and efficiencies with some dedicated study. Crucially, also, in making these estimates, we're not simulating physics backgrounds or beam-induced backgrounds. So it's at least believed that, especially at higher energies, the beam-induced backgrounds are plausibly under control. And our lack of simulation of physics backgrounds, of course, that's very important. But as I think we've seen from CLIC and also from extrapolation to the 10 TeV muon collider, it should be possible, because the backgrounds are of the same order as signal, should be possible to beat down backgrounds without appreciable loss of signal. So I just want to emphasize these are some ballpark numbers to sort of set the discourse and to give you a sense of what a muon collider may be able to achieve. So if you play this forward into a coupling fit, you get the following, which is just the sort of kappa 0 10 parameter fit. So that's no invisible or untagged branching ratios and no combination with the HL-LHC. And this is with comparison with projections that came from the 2019 sort of summary of the future collider proposals. So because this is the result of our sort of ballpark studies, I would encourage you not to take the muon collider projections at 10 TeV too seriously, but it does indicate that it should be possible to achieve very interesting precision in Higgs couplings at a muon collider operating at reasonable energies. Okay. I also want to emphasize that the result of this fit, this is just from looking at sort of on-shell processes. You're making a Higgs and letting it decay, and because of the fact that you have enormous energy growth of irrelevant operators from colliding the elementary muons themselves, that off-shell contributions and contributions from irrelevant operators, that freedom to constrain Higgs couplings is likely to be very powerful. So the Higgs without Higgs program in a muon collider is likely to be even more interesting in some sense than this sort of direct on-shell production. I can give you one example of that that's very concrete, which is looking at the Higgs coupling to top quarks without necessarily producing Higgses in the final state. So you could think of this as looking for unitarization of TT bar, of longitudinal vector scattering into fermions, which is something that we would like to see in the standard model, but also as a measurement of the Higgs coupling to top quarks. So I've chosen this as an example of sort of Higgs without Higgs because you expect the Higgs coupling to top quarks to remain an interesting target after the HLLHC, which is expected to get to about 6% precision. But also even if, for example, there's a Higgs factory like FCCEE that's built in the run up to a muon collider, although that collider, a Higgs factory will get incredible precision, for example, in the Higgs vector couplings, the Higgs TT bar couplings will not have the same level of precision. So it's still an interesting target, even if a muon collider comes after a Higgs factory. And so if you just do the simplified picture of imagining that the top Yukawa coupling differs by some amount from its standard model value, then of course at high energies, the scattering of longitudinal vectors into TT bar is growing with energy proportional to the deviation. And so you can just go ahead and look at the TT bar invariant mass distribution. And these plots are showing the effects at 14 TeV for unpolarized and polarized beams. And of course, there are interesting shape distortions. The only things I want to point out is that at very high, the high tail of the invariant mass distribution, there is, regardless of the sign of the deviation, an increase relative to the standard model from the non-unitarization of this process by the Higgs. There are also contributions at lower invariant mass whose sign depends on the interference. And so in particular, negative deviations lead to constructive interference and positive deviations lead to destructive interference. And you can, of course, augment these effects by using polarized beams. So the conclusion from a very simplified analysis, on the left, it's just showing the integrated luminosity you would need as a function of your center of mass energy to achieve certain precision, whether you have polarized or unpolarized beams. And on the right, it's showing for two center of mass energies, the constraint envelope you would get on the Higgs coupling deviations, again, as a function of your integrated luminosity. And so, to the extent that we sort of expect to get 6% precision after the HLLHC, this tells you that a muon collider operating at 10 or tens of TeV with tens of inverse Autobarn, you can do better by a fair bit than what you would have already known from the LHC. So this is just one example of the idea that a Higgs without Higgs program is very compelling at a muon collider. Another good example, turning from the standard model to more explicit or direct production of new physics, is leveraging that longitudinal fusion of vector bosons to produce new degrees of freedom. So here I want to highlight, this is a paper by, two of the authors are here today. This paper, I just want to say, this was in some sense the original muon collider enthusiasm generator, because after I think a lot of quiet in muon colliders, they pointed out that there are vast gains that are potentially achievable at a high energy muon collider, I think before sort of recent uptick in activity. So it's a fantastic paper. It certainly was responsible for sparking a lot of my interest in the topic. And the basic point is just that there's an interesting rate for longitudinal vector boson fusion into a Higgs, but that's even more interesting if you have heavy scalars. And so here they consider just the case of a scalar that gets its coupling to the standard model by mixing with the Higgs. And so of course there is large enhancement of that rate at large center of mass energies. And what the right plot is showing you then is, depending on the center of mass energy of a collider, with the same luminosity assumptions we've been using, the parameter space that you can cover as a function of the mass of the scalar and the mixing angle. And the dashed lines in this case are showing you sort of two reasonable parameterizations of the mixing angle, depending on whether the scalar gets a VEV from its own potential or from its connection to the Higgs. And so that sort of gives you an envelope of interesting mixing angles. And what you can see is within that envelope, even a 6 TeV muon collider can exceed the reach of 100 TeV proton-proton machine. So this is really exemplifying the power of longitudinal vector fusion at a muon collider. And the other thing that's worth pointing out is this is a nice, we focus these days on Higgs precision as a way of accessing new physics. In this particular scenario, of course, there are Higgs coupling deviations coming from the mixing as well as direct production. But the sensitivity you get from a muon collider for direct production or discovery is order of magnitude better than the precision you would get from looking at Higgs coupling. So this is a situation where even in a post-Higgs factory era, there would be much to be gained by building a high energy muon collider. There's lots of other deviations on this picture that you can put to good use. I just want to talk to them about them briefly in the interest of time. One of them is rather than necessarily making new scalars, you can also even just look for their quantum effects. And so the sort of benchmark for this, which is shown up in a lot of different physics cases for future colliders, is to imagine a Z2 symmetric singlet, so one that only couples as its square to the Higgs. And this, of course, is a nice model for getting a strongly first order electric phase transition or dark matter or naturalness. It's often called the nightmare scenario, because if you produce this thing directly, it's only pair produced, and it's only pair produced through an off-shell Higgs, which makes it incredibly difficult to constrain, in part because missing energy, is a relatively high background final state. But because you have, again, these processes where you have large contributions from longitudinal vector boson fusion into standard model final states, it's actually very interesting to look for effects of such a singlet as corrections to the fusions of longitudinal vectors into standard model final states. So one thing you can do is look for quantum corrections to longitudinal vector fusion into TT bar. And the effect of those quantum corrections, although they are modest in most parts of the invariant mass distribution of the final state, of course, when the invariant mass of the TT bar pair crosses threshold for the scalars, there's a feature in the distribution, just as there's a feature in gluon fusion to the Higgs as you pass through the top threshold. And that feature then is a very small bump, which you can look for on top of the invariant mass distribution. And so these sorts of effects, they're not interesting at any other collider, but in a situation where longitudinal vector fusion is a sort of dominant contribution to the final state, these effects can actually be used to look for new physics. So to my knowledge, this is a new way of looking for these degrees of freedom that is really only interesting in a muon collider. You can, of course, also do what we're normally used to thinking about doing at the LHC or the 100 TeV collider. You can also produce these things on shell. And as I said, this is a much harder game because you produce them only through an off-shell Higgs boson, and missing energy is not a zero background final state. So here I would say the prospects of a muon collider are really comparable to a proton-proton machine. What I'm showing you on the left is the reach and the mass of the scalar as a function of its coupling to the Higgs. And the dashed line is a sort of benchmark that corresponds to the scalar getting all of its mass from the Higgs. That's kind of the line, for example, that you want to live around if you're using this to explain a first order electric phase transition. And so the conclusion here is that coverage of this, the interesting part of the scenario, requires muon colliders above tens of TeV. But this is just the result of initial studies and would be useful to dig into further. As long as you're thinking about invisible final states, of course, it's worth talking about dark matter. And here, a good example is the paradigm of minimal dark matter, where we just imagine electric multiplets whose thermal abundance comes from their electric interactions. And they're very powerful prospects now for muon collider for minimal dark matter, just because there are large electric production rates and the relative backgrounds are not that large compared to a hadron collider. So this is just showing you actually the discovery reach to be a little more optimistic. For both the optimistic and the conservative luminosity targets I sketched for various center of mass energies and various electroweak quantum numbers of the multiplets. And there's a sort of white line in each of the bars, which is the thermal target. And the fat bars are showing you the reach from a direct search projection, and the sort of narrow bars on the bottom of each of those are showing you the potential reach from a charged stub search that looks for production of the charged particles followed by decay to invisible final state. And the conclusion is, especially for the smaller electroweak multiplets, that even a collider operating at 10 or 14 TeV should be able to push through the thermal target of most of the interesting cases. And so this is much like Click, I think, really awakened us to the possibility that these high energy lepton colliders are dark matter discovery machines. That's also borne out here for muon collider. I want to give one more example that I think nobody has really thought about. So it's a fun example of the new things that are possible in a muon collider, which is, and I apologize to Adam because I know he's not friends with supersymmetry. But wouldn't it be great if you could discover supersymmetry not by discovering the superpartners of the standard model, but actually by discovering the mechanism itself, the universal property, which is that there is a Goldstone fermion of spontaneous supersymmetry breaking. And this has always been something that you could think about in situations with low scale supersymmetry breaking, because the coupling of the Goldstino which of course becomes the longitudinal mode of the gravitino, that coupling is suppressed by the SUSY breaking scale. So for low scale SUSY breaking, that coupling is not too tiny, and you could think about producing the gravitino. And indeed, there are universal couplings of the gravitino to standard model particles that are independent of the mass spectrum of superpartners. So it sort of provides, again, a very concrete probe of the supersymmetry breaking hidden sector. Now, the reason why we normally don't talk about this at the LHC is that the bound you could get by looking directly for the gravitino is always weaker than the bound you would get by looking for superpartners in the standard model because of their abundant production cross sections. But because the production of the gravitino goes like S cubed, that means if you get a high energy muon collider and you're able to use all of the energy of the muons, the rate is growing enormously as you go up in energy. And the backgrounds, of course, are only logarithmically growing. So the higher energy lepton collider you build, the more and more you're able to discover the gravitino directly. And to my knowledge, it's really only at a muon collider operating at tens of TeV that you could first discover the gravitino before you had any access to the superpartners of the MSSM. Okay, so this is just a nice example of something new you can do at a muon collider. The last comment I just want to leave in terms of thinking about new ways of thinking about the physics case for muon collider is higher order effects are also interesting because backgrounds are small. So we focus a lot on producing new physics through its electroweak quantum numbers. That's a sort of natural thing to do in vector boson fusion. But of course, it's also possible to look for higher order effects. So a good example is you might worry that it's never interesting to look for gluinos, for example, at a muon collider because they carry no electroweak quantum numbers. But of course, you can always produce a very high energy QQ bar pair and then just Bremsstrahlung a gluino pair off of the quarks. And even though that's a higher order process, it's nonetheless interesting. And it seems, at least by a very simplified analysis, to give you discovery potential for gluinos beyond what the LHC will leave us with. All right, and the last thing is just turning away from sort of direct discovery of new physics or probing electroweak symmetry breaking. I think things that we care about in the post-Higgs discovery era. The last thing I just want to comment on is, in the time scale that we have for building a muon collider, there are many, many experiments that will happen that will could give us interesting indirect evidence for new physics. And it's very important to understand the sense in which a muon collider could then help us to sweep through the scale that these experiments might indicate and discover the physics directly. So one example I want to highlight is actually physics that might contribute to the electron EDM. So within the next decade or maybe 2 decades, various improvements in electron EDM experiments will give us like a 3 order of magnitude increase in reach relative to what we have now, to the point where they are sensitive to particles around 20 TeV that are just running in bar Z diagrams. And of course, if you just draw a little square on the bar Z diagram, that same thing now gives you an interesting indirect effect at a muon collider. And so to the extent that muon colliders, as we've seen, are very powerful probes for new physics, even by looking in standard model final states, it should be possible, even with a muon collider at 10 TeV, to discover more evidence or even directly produce physics that could show up in electron EDM. And of course, I think what's been on people's minds very recently is muon G-2. So there's a lot of very nice literature about the prospects for discovering explanations of muon G-2 at a muon collider. I expect we will know a lot more about how excited we should be about that within the next few weeks, as well as there's been some work, of course, about possible explanations for flavor anomalies. So there's just because muons are an interesting physics object, colliding them gives us access to a lot of possible indirect evidence that we've had for new physics. Okay, so that brings me to the end. At least for me, the answer to why now is that these high energy muon colliders could potentially be the best of all possible worlds. They can give us precision because of the low backgrounds, but they can also give us incredible reach and energy. And we're at a really interesting time that we have the opportunity to develop the physics case from the ground up and shape the proposals for accelerators and experiments as they come together. I think the qualitative conclusion that one can draw by looking at these various examples is that a muon collider operating at tens of TeV, including just 10 TeV and tens of inverse autobarns, can really comprehensively cover a lot of both the standard model and beyond the standard model physics that we're interested in the era following the Higgs discovery. So there's, of course, a famous quote by John Muir, which is, "The mountains are calling and I must go." So we repurposed that a little bit for the purpose of our muon collider investigations. I think it's fair to say that the muons are calling and we must go. So thank you very much.
Thank you very much, Nathaniel, for the entertaining and nice talk. I would take questions. For the previous talk, you can raise your hand in the chat or just speak up. So I don't see anyone in the chat, maybe due to my lack of familiarity with Zoom. No. Okay. I mean, of course, needless to say, we take also questions for like for the previous talk or for the ensemble of the two. I see Daniel is still here.
Yes, I am.
Maybe I can ask a stupid question. So the way I covered my eyes and ears when you were talking about gravitino, so I don't know anything about this. But yeah, about the Higgs. So why the precision of the Higgs coupling to muon is so low in the muon collider? It's so it's
so I mean we are not using. I mean, if you had 125 GeV muon collider, of course you would get astonishing precision because you would be probing that directly. But here we are the only direct access we have to it, right? We're assuming that we are taking the dominant mode of vector boson fusion production of the Higgs, and then it's just the decay. And so this is largely a consequence of the very naive assumptions that go into this initial blocking out, right? So the acceptance times efficiency of this Delphi's card, which doesn't get us access to forward objects, and then we have relatively crude tagging assumptions, and so that's what gives that number. But indeed, going beyond just production of a Higgs and then decay into muons, using other indirect probes, using sensitivity irrelevant operators, putting those into this analysis would considerably enhance the sensitivity.
But maybe going back to my previous question I had to Daniel, so would it make sense to run maybe at 125 GeV and just to produce the Higgs as a resonance?
Yeah, and indeed, that I mean, the original, I obviously didn't survey the literature in my talk, but many of the original proposals by Tao Han, for example, for a muon collider, the idea was to have it at the Higgs. And I think there is a very interesting physics case. There's a question of, if you build a muon collider that can operate at 125 GeV, does that give you a nice foundation for then building to a higher energy collider? And I think maybe Daniel can speak to that.
Yeah, so my question is, yes, let's say we know that there is probably new physics in the Higgs coupling to muons. Is there a switch, the lever that you can pull and make the energy 125 GeV?
Well, for 125 GeV, you have to design the collider in a somewhat different way, because you want a very small energy spread. I mean, the 1 per mil obviously would be way too large because the resonance is so tight. So what you would do is you would forego the final cooling stage, which means that your beam transversely is larger, but you have a smaller energy spread. It has problems of its own in the design. However, we think that if there is a strong physics case, yes, I mean, one could work on that. Now, the main reasons why we don't do that is because one has to establish that the physics case is very strong compared to other Higgs factories that are more mature. And also, but in Europe, there's certainly support for some other proposal. I think also in the US for a Higgs factory, and it may be good to see when to compete and when to still hold still. But we are happy to have that developed, and I think within the test facility discussion, it will come up again. Do we need to, in the longer term, do something on longer term on the Higgs factory? Yes, absolutely.
Thanks.
So given that we talked again about test facility, so question for Daniel. I mean, you said it, but I already forgot it. The test facility would have a map-like technology for for the muons?
Yes, I think as far as we can judge, the lemma scheme looked attractive initially, but during the review for the European strategy, there were 2 flaws in the design that I saw. And with the looking at the parameters, there's no consistent parameter set that actually would give a luminosity comparable to the proton scheme. The main, I mean, maybe if you have a sec, the main reason is that it is very costly to produce a single muon pair. You can do the calculation yourself. It is of the order of a fract. I mean, we talk about millijoules for that. It's a substantial energy, and that means that your muon current is limited, and that's just the basic cross section. I mean, and it's really the ratio between Bremsstrahlung, which makes you lose all the positrons, and of muon pair production. And this ratio is very, very large. So 10 to the 5, I mean, only 10 to minus 5 of the events actually produce a muon pair. And because of that, the current has to be low, and then multiple scattering kicks in. And the only way you would overcome that is by starting with a very, very large charge in the positron beam, in the bunch. And that charge seems excessive. And also the stored energy in a proton beam, in a positron beam, sorry, would be of the order of 20 megajoule or something. And you need 100 passages. So you need 100 of these bunches lined up. So, okay, but we did not yet find a configuration that works. It might be there is an option, but nobody came up with a sort of putting some numbers on paper that all made sense and that lead to a reasonable luminosity. So because on that, I think it's protons, because everything looks ambitious and hard, but it looks in a way we always felt that, yeah, maybe it could be done. It's just difficult, not excluded.
Okay, thanks. The challenge being the cooling there.
The cooling, yes.
Like what's the biggest challenge there? What you would say is the biggest challenge there?
It's the newest. So the cooling, yes, it is very important. There's some quite intense engineering, because you have to put all of these components together. It always looks so easy, but then the devil is in the detail. I mean, it's like if you design a detector and then suddenly somebody annoys you and says, but you have to have vacuum. So where do you put the vacuum? And then suddenly everything goes berserk and it becomes a problem. So the integration is very difficult. For the physics, I hope we master it. So we should trust the theoretical calculations, but getting a high field in a normal conducting structure, in a strong, so X-rating RF field, in a strong magnetic field is very tough. And a demonstration of a single, of some cavities has been done, but it needs to be done routinely. It needs to, and this is black magic. This is surface physics. There is all sorts of things where people have to do it experimentally. You cannot trust. You don't know what to exactly calculate to anticipate what the effect is. You have some rough ideas. It could be energy flow, power flow. That's like for click or the ISC. I mean, it's not straightforward to say where you end up with the grain. But then also at high energies, what is critical is to get efficiency and to get cost-effective components. Because, I mean, let's look at the FCCHH. I think technically, except for the magnets, which are not yet there, maybe we didn't find something in the design that didn't work. There were lots of big problems with the collimation, many challenges, but we managed to design things so that I think they can all be addressed. What is left is the magnetic field and the fact that these magnets are very expensive and that the costing we made was a target. It was not based on a prediction at this very moment. It was a wish. And so we have to, for such a collider, we have to make sure the cost is something that you could expect to really pay for. I mean, it's otherwise it remains a dream. So unfortunately, that kicks in. That's also why we are a little conservative and promise 10 plus and not 30 TV, because we would like to do a stage where we think that, yeah, you can see the US and Europe and Asia together could build this.
Thanks. So are there other questions for either of the speakers?
well, maybe I have one, but it's a bit silly and unfair at this stage. So if you were given all the resources that you needed, when would you estimate it possible to start taking data? Let's say from today you have
Okay.
all the money.
You saw the schedule. It was a technically limited schedule, which takes 15 years from
Yeah, I
now
saw that.
to
I saw that. Yeah.
start of construction. And then you would maybe assume 7 years of construction, typically. We didn't do a planning, but you end up with something of that order, maybe a little more for cost reasons. So you talk about less than 25 years. Now, the assumption there is we get all the people that we need and the resources. We get the highest priority. So sort of if I ask for somebody to work on that,
Yeah,
that person will work on that and not be considered for Halloumi instead or something else. So if you look at that, it would mean that if you're very optimistic, before the end of the LHC operation, Halloumi, you would be actually able to start construction. Now, maybe that's a little ambitious, but what you could hope for is that realistically, before the end of LHC operation, the currently foreseen 38, you would actually know that this is the next project that is feasible and needs to be constructed. And I suspect Halloumi will operate for longer than foreseen.
well, thanks. I mean, it's actually, to me, it sounds encouraging.
Yeah, and I have to say also this plan technically limited means the resources and that we don't find an obstacle that takes us some years to overcome, because we first have to have the clever guy who under the shower suddenly discovers how to solve it.
Sure, but you don't, I mean, you're talking about like unforeseen obstacles, not issues that you already know and need some creative solution.
Yeah. No, we know of issues, but they all seem. I think that the one with the neutrino radiation, for my mind, was the worst, and everything else should be solvable by technology. And we hope we have a solution for the neutrino radiation. And if that's true, I think the detector people will be able to deal with the background that is left over.
Sure.
And will be more intelligent detectors, more timing track clever algorithms that identify tracks that are from the background as coming from the background, not just pretending everything is from the event. So that is solvable, and the rest I hope as well. Just takes the effort.
Thank you very much for kindly answering my unfair question.
No, it was a good question. I think it's given the long time scales that we see in some plannings.
Yeah.
It's a very valid question. You wonder when you turn yourself 100 or or more during this process. Okay.
And it may, if I can just add to something else to think about is that you could put 10 TeV muon collider on the Fermilab site without significantly exerting yourself, right? And so that may also turn out to be something that could make a time scale reasonable for our physics careers.
Yeah.
I have one more question to Nathaniel.
Please, Adam.
So about except for Higgs physics, what is like purely standard model physics? Yeah, that you can learn something new from, qualitatively new, using the muon collider.
I guess my question to you is exactly how do you want to prescribe standard model physics, right? So
like there's no new physics, no new particles. Yeah, so that are.
So I mean, so one thing, for example, is so irrelevant operators. If you say Higgs physics, I mean, we have to assume there is something that could be a deviation from the standard model. So you'll allow me irrelevant operators?
No, just
why? Well, then, Adam, why measure anything if your prior is?
No. I have the question. Just my question is whether, like, for example, I don't know. So if you take the 100 TeV collider, so I think you can learn something about neutrino radiation. You have this qualitatively new. So you have neutrino radiating W bosons. So that's.
Oh, of course. And I mean, analogous statements are true at sufficiently high energy muon collider. So there's nothing about that physics case that is unique to proton-proton machines. Indeed, the ability to measure the cubic and the quartic Higgs, okay, so you would file that under Higgs coupling measurements. The fact that you have, so the, normally I would say the sensitivity to lepton flavor violating processes is a BSM probe, but of course there's great sensitivity to lepton flavor violation that is complementary in sensitivity to many of the low energy experimental tests that we'll have in the coming decades. So I think that's also very interesting. Indeed, measuring things, I would say measuring the electroweak boson PDFs of high energy leptons is a very interesting, that's an emergent property of the standard model at high energies that will be measured and is very interesting. So yeah, I think I would argue essentially anything you could do at a sufficiently high energy proton-proton machine, you can do with as much clarity or more clarity at a muon collider, simply because
But is there something you can do only with muon collider and still?
Well, again, lepton flavor violation. So there you are leveraging the fact that you have a muon initial state. Again, the electroweak boson content of high energy leptons is also a unique property of a muon collider. Yeah, I'd say to me, even if you just wanted to study the emergent properties of the standard model, those are all very interesting.
Thanks.
Okay, thanks. Then maybe let me ask one last question on a more optimistic BSM side to conclude with more optimism. So given that you got all this broad picture by coordinating this effort, is there some energy scale, like for the center of mass energy, that you would tell to the experimental colleagues, like you should achieve at least the center of mass energy because we can test this, that you think is a more motivated BSM case for some reason than others?
Yeah, and I would say I tried to make a sort of general statement at the end that tens of TeV, because indeed, so what we've tried to define are sort of thresholds by which you would learn something qualitatively new. So those thresholds could be covering the thermal abundance of minimal dark matter scenarios, or they could be measuring various Higgs properties to precision that would decisively tell you about the electroweak phase transition, these sorts of thresholds. And the answer is, for a given scenario, the threshold, however you define it, sits between a 10 TeV, typically between a 10 TeV muon collider and a 30 TeV muon collider. But I think something that's come out of the study, I went to it thinking, well, maybe the answer is going to be you need a 50 TeV muon collider and we should therefore advocate for it. But I would say you will get a sort of order one fraction of the interesting thresholds with a 10 or 14 TeV muon collider, which is encouraging because I think, as Daniel has emphasized, those are realistic, potentially realistic targets that we could imagine focusing in international collaboration. So to me, the outcome of this exercise, 20 TeV would be great, but there's nothing to suggest that you have to have 50 TeV to do to really have a comprehensive successor to the LHC.